In 6.1, we're going to look at right triangles and how they serve a function and a purpose and a way of looking at some of the applications we're going to use in trigonometry. So let's take a look at a right triangle. And a right triangle, of course, the only thing that's unique about a right triangle, which makes it a right triangle, is the fact that it has a right angle. One right angle. In fact, no triangle can have more than one right angle. If you had two, 90 plus 90 is 180, and all three angles should add up to 180 in a triangle. So it's impossible. If I add another right angle over here, they don't meet anymore. They wouldn't meet. We'd have two sides that run parallel to each other. So, if we think of A as being the angle that we're talking about, and so we want to put these sides that we have. What's unique about a right triangle is we have the two sides that come to give us the 90-degree angle. We label those A and B, and you could have them in the other direction, but for this particular thing, we're putting A over here, B here. These are the legs of the right triangle, and then the side that connects those two, the two that are making the right angle, is called the hypotenuse. So when we talk about this angle, we see A here as being opposite of that angle, right? This angle, in fact, doesn't touch this side at all, whereas the angle here is made up of the other two sides. So we say that A is the opposite side of theta. If my theta was up here, then B would be the opposite side. So it's all in relation to where the angle is that we're considering. So with angle theta, B would be the one that's adjacent to it, even though there's two that are adjacent to it. This one has a special name already. It's the hypotenuse. So we just call that one the hypotenuse, and we say this one's adjacent to the angle theta. Just to give you an idea of what we're doing here and how this connects to what we've talked about, this is just a quick little explanation. If I have a circle in the middle of an XY coordinate system, and this is my terminal side, this is my initial side, and we have this circle here, this ray is eventually going to intercept at this circle. And that intersection point has an A value and a B value. So it has a height and it has a base here. And I do want to just point out that even if we kept going here, we could stop at any point and it would again create another triangle. And that what we see here is that my sides will be proportional no matter how large that triangle is. In other words, the ratio of, say, A over B is equal to the ratio of A prime over B prime. B prime being the whole length of this side, A prime, of course, the whole length of this side, for the larger triangle. So what we see is we have proportionality. Whatever the value of A is, whatever the value of B is, for each of these, if we divide them, they are proportional, meaning they are equal once we divide them. We're going to keep that in mind going forward. This is going to come up later, but just wanted you to see the connection between this and the circles and the things we've been doing with the circles, with the angles in the previous section here. All right, so let's introduce, in terms of this triangle that we get, some trigonometric functions. These trigonometric functions are ratios of different sides of this triangle, or can be looked at from that perspective. Sine is the ratio of the opposite side divided by the hypotenuse side. Whatever that ratio comes out to be, that would be the value of the sine of theta. Also, the cosine would be the adjacent over the hypotenuse. I want to point out that hypotenuse in a right triangle is always the largest side. So for sine and cosine, these values are always between 0 and 1. Always between 0 and 1. Because the larger number is always on the bottom. Tangent, on the other hand, is equal to the opposite side divided by the adjacent side. So opposite being A, adjacent being B. That's the tangent of theta. So we have sine, cosine, and tangent. These, of course, are the shortened versions of those words, but those are those mysterious buttons you see on your calculator. When we also have the reciprocals of these. So cosecant is what CSC means, is actually the reciprocal of sine. And secant is the reciprocal of cosine. So in other words, you'll notice that these are just the same sides but reversed. So hypotenuse over opposite, hypotenuse over adjacent. And since C now is guaranteed to be the larger number, because remember, C is always the hypotenuse, these will be greater than 1. Going to tangent, tangent is opposite over adjacent. Cotangent is just adjacent over opposite. All right. All of these are going to create ratios, and which we can turn into decimals as well, but the ratios tend to be a little more interesting. So let's put this into practice. Here we have a right triangle, and I know 2 of the 3 sides. We know the adjacent side is square root of 7. The opposite side is 3, but we do not know the hypotenuse. But luckily, we have the Pythagorean theorem, so we can actually come up with that first. So that's our hypotenuse. C squared equals A squared plus B squared. I'm just going to write that out. Then we have C squared equals A, which would be 3. So 3 squared plus square root of 7 squared. And squaring those out, that gives me 9 plus 7, which is 16. So C squared is equal to 16. If I want to find C, then I would take the square root of that. Of course, that gives me positive and negative 4, but of course we can't have a side that has a negative measurement. So we see that C is equal to 4. So I'm going to go ahead and put that in there. We have that value. Let's look then at sine. Remember, sine was opposite over hypotenuse. And I wanted to give this back to you before, but when it comes to sine, cosine, and tangent, there's a little kind of thing you can do to remember what they are. And it's the SOH, so, ka, toa. And SOHCAHTOA, which sounds like, well, I don't know, something, but you can memorize that. And what this is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. So for sine, we want to go opposite side of theta. Remember, theta is right here. And so the opposite would be here. Opposite over hypotenuse would be 3 over 4. Cosine, adjacent over hypotenuse. So in that case, that would be square root of 7 over 4. And then tangent, opposite over adjacent, is 3 over the square root of 7. Which most of the time we don't like to leave square roots in the denominator, so we like to, what we call, rationalize them. Turn the denominator into a rational number, meaning a number not involving a radical. So if I multiply both the top and the bottom by the square root of 7, that gives me 3 square root of 7. We can do this because this has a value of 1 here. And square root of 7 is 7. We can't simplify this anymore. So we just say it's equal to 3 roots of 7 over 7. Sometimes 3 can cancel with 7 or whatever you have down there. But in this case, no. Once we go to the other ones, these are just the reciprocals of the previous. So cosecant and sine being reciprocals, 4 over 3. secant being the reciprocal of cosine. That's 4 over square root of 7. So if we multiply again, square root of 7, top and bottom, that's 4 root of 7 over 7. Again, can't really cancel any of those. Tangent was 3 over root 7 before we rationalized it. So I'm just going to take the original one and say cotangent is square root of 7 over 3. Great. So these are my 7 trigonometric functions for this particular triangle. One thing you can keep in mind to try to remember some of these things, sine, you want to think sine, cosine, and tangent. These are my originals, right? These are these are all the reciprocals, right? So that's one thing to remember. But also keep in mind that the reciprocals actually have different letters at the beginning. So cosecant of theta has a C, and this has an S. Cosine has a C, and secant has an S. So they're not set up where you might go to where you match up the letters. They're actually opposite. The sine goes with the one that starts with a C, and the cosine goes with the one that starts with an S. And cotangent, in and of itself, has the word tangent in it. It's just cotangent. So that's how you can remember that tangent and cotangent are the two with the relationship. Okay, so as we saw in the previous, if I know 2 of 3 sides, then I have the information to get the third side. So if I'm told a triangle has a sine theta, we don't know what that theta is, what that angle measurement is, doesn't really matter. But for this particular triangle, remember sine is opposite over hypotenuse. SOH, so, ka, toa. So this is opposite over hypotenuse. I know that it belongs here and that my hypotenuse has a value 5. That's enough information for me to go 2 squared plus b squared should be equal to 5 squared. 5 squared being the largest side. And so that's 4 plus b squared equals 25. So b squared equals 21. If we take the square root of both sides, we see that b is equal to the square root of 21. Always looking to maybe simplify that if we can, but there are no perfect squares that go into 21. 21 is 3 times 7, and that's about it. So we're going to use that, and now we can come up with all the other. We have sine. Sine theta we saw was 2/5. That was given. Cosine is going to be adjacent. So adjacent to my angle, that's going to be the root 21 over 5. And then the tangent is going to be 2 over root of 21, which rationalizing this, that gives me 2 root 21 over 21, and 2 doesn't even go into 21, so I can't simplify those numbers at all. Then sine, the reciprocal of sine, is the cosecant of theta, and so this would be 5 over 2. Secant goes with cosine and is reciprocal. That's 5 over root of 21, so we can already see that this is going to be 5 root 21 over 21. Just rationalizing the denominator there. And then cotangent, well, that's going to be just the reciprocal of the original, so square root of 21 over 2. And those are my trigonometric functions for this particular triangle. Another thing we see with our trigonometric functions is that if we're dealing with an acute angle theta, so a theta that's between 0 and 90 degrees, we see that it's equal to what is the cofunction of the complement of theta. So like sine and cosine have a relationship, tangent and cotangent have a relationship, and secant and cosecant all have a relationship. And this kind of goes to some of their names. But what we see that is if I find the let's see if I can find this here, my pointer. If I take the sine of theta, it's going to be the same as 90 minus theta, taking the cosine. And the same is true vice versa. Cosine is equal to 90 minus theta's sine. Tangent will be equal to cotangent if we subtract it from 90, and vice versa, secant and cosecant. And if theta is measured in radians, then we can replace 90 degrees with theta over 2. So, finding trigonometric functions of values of a complementary angle. So let's say that we have, we know that the cotangent of 60 degrees is 0.0404. Find the tangent of 22. Well, we can notice that 90 minus 68 is 22 degrees. So if the cotangent of 68 degrees is equal to 4040, then the tangent of 90 minus 68 degrees, or tangent of 22 degrees, is going to be equal to the same amount. Also, we can see cosine and sine. Those are complementary with the theta minus 90, or 90 minus theta. So if the cosine of 72 degrees is 0.3090, then the sine of 72, or 90 minus 72, which is 18 degrees, is also equal to that same number. As we explore these more and more, you're going to see these relationships begin to make sense. Some of these you just have to kind of accept for the current moment, but yes. Okay, so if we know that A is 23 degrees and C is 5.8, can we find the other sides? Well, for one, I can find the other angle, right? If this is 90, if this is 90 and this is 23, 90 plus 23 is 113. So let me write this out. 90 plus 23 plus, we're just going to say B there for the angle B. And sometimes we'll put a little angle symbol next to it. Should equal 180. All angles added up in any triangle should always equal 180 degrees. So combining these together, this is 113 degrees plus angle B, and that's still equal to 180. So if I subtract 113 from 180, that gives me 67 degrees. So angle B is, we know, 67 degrees. All right, what do we do to find A and B? To solve a triangle, we need to not only come up with what all the degree measurements are of that triangle, but also all the side lengths. So we need to figure out what A and B are. And luckily, the trig functions can help us do that. First thing you want to do is make sure your calculator is in degree mode and not radian mode. So if you go to the mode button on your calculator, which for the TI-8384 is near the top, hit mode and then scroll down till you see radians and degrees, excuse me, and switch it over, make sure it's in degrees, that it's highlighted. Then let's write out a trig function. So sine of 23, I'm just going to start with the angle there that I know, is opposite over hypotenuse, so that's A over 5.8. We can solve for A by multiplying both sides by 5.8, and that gives me 5.8 times the sine of 23. This is something you can just type directly into your calculator. Once you have it in degree mode, 5.8 times sine of 23 degrees. And what we get, decimal-wise approximately, rounded to the first, is 2.3. So A is approximately 2.3 units to C's approximate 5.8 units. To find B then, I could use cosine. We say the cosine of 23 is equal to, the B over 5.8. And then, same thing, multiply both sides by 5.8. So we see B is equal to 5.8 times the cosine of 23 degrees, which is about 5.3. So B is about 5.3. Notice that I could have also gotten this, now that I knew A to be 2.3, we could do the tangent. So instead of using cosine, I could have just gone, well, tangent of theta is opposite over adjacent, TOA, so 2.3 over B. And this just means I've got to do a couple extra things here. Got to get B out of the denominator, right? And then I have B tangent of 20, I meant to put 23 degrees there, not theta, 23. B tangent 23 is equal to 2.3. Interesting enough, I never saw that connection. But B will be equal to 2.3 divided by the tangent of 23. And if you carry that out, 2.3 divided by tangent of 23, you get the same thing, approximately 5.4. The only differences here are rounding issues. And 2.3, I think if I was going to do tangent where I'm using a number that I know is approximate, that I had to round, you can see why this is coming out slightly different. This actually comes out as 5.41. But the more we had taken out the 2.3 out to several decimals, let's see, 5.8 times sine. That was 2.3, but 2.3 was rounded, and then the cosine was 5.3, but that was correct. Yeah, so you could see that because these are both rounded numbers and I'm using them to get the tangent, they're coming out slightly different, and that's okay. These are all rounded values. But since I found the lengths of all the sides and all the angles, I've solved the triangle. Here's another triangle that we need to solve, but in this case we're given two sides and we don't know either of the angles. So how do we find this? Well, I could find the third side because I have two of the three. So maybe let's start there. I know that c squared will equal a squared, so 9.5 squared plus b squared, 3.4. And so that pretty much gives us something straight off there. 9.5 squared plus 3.4 squared equals, this is 101.81. Of course, that's c squared. Let's take the square root of that, get the approximate value. And when I get the approximate, I just try to put squiggly lines there to just show that it is that. And so we get 10.1 approximately. So C is about 10.1. But I'm going to go with the hard sides that they gave me there when I look for my angle. So, and I'm going to start with angle A, though we could also go with B, doesn't really matter. But I know that I've got these two sides. These are the ones that were given. And so I'm going to use those any way that I can. Probably the easiest way is for me to do the tangent. The tangent of that theta, and actually, let me put, instead of theta, let's put the tangent of angle A, little angle symbol next to A there. And I know that that is the ratio of the opposite over adjacent, so 9.5 over 3.4. 9.5 over 3.4. How do I solve this for the angle, though? Well, there's above the tangent sine and cosine values is you're going to see tan -1, and then cosine -1 and sine -1. What that means is doing the opposite operation, going from one thing to another. It's the inverse of tan, the inverse of tan. So if I, on both sides, take the inverse tan to the -1, which is not, we don't move it to a denominator or anything like that. It's simply a symbol for the inverse. The tan and its inverse undo each other. And so that actually leaves me with angle A. And I have angle A being equal to the tangent inverse of 9.5 over 3.4. So if I do that on my calculator, second tangent, so I'm taking the invert tan of 9.5 over 3.4. That will actually give me the angle measurement of A. The angle measurement for A is 70.3. And that's approximate. It's not exact. There's more decimals there, but that's a pretty good rounding of that. Once I have that, I know this is 70.3, and I kind of confirm that that's a little less than 90, right? It's not quite 90, but it's a pretty big angle. So I can expect this one to be a small angle. And if we go 180 minus 70.3 minus 90, or actually, sorry, we can just take, if this is 90, we know these have to add up to 90, because 90 plus 90 is 180. So if I just go 90 minus 70.3, I get 19.7, and that would be the angle up here. So angle A is 70.3, angle B is 19.7, and C, the hypotenuse, is 10.1. Where we really see the helpfulness and the application of trigonometry and all these trigonometry signs, cosine, tangent, and all that, is in some real life, real applicational problems, where we can make some measurements that we're aware of and use other methods to help me figure out what distances might be. So here's just an example here. We want to determine the height of a cloud at night. So a farmer shines a spotlight upward to a spot on the cloud. The angle of elevation to the same spot on the cloud from a point located 150 feet horizontally from the spotlight is 68.2. And so from this, we're going to try to figure out what the height of the cloud is. So we have this spotlight that's being shown upward. And so it's making an angle there. So it's pointing it toward a spot on the cloud. And then we know what the angle of elevation is to the same spot on the cloud from a point located 150 feet horizontally. And there's instruments we can use to do these type of things. I'm going to choose a different color here. Is 68.2. So we can use, I can't remember what they're called, but we use this instrument to create this angle. And we also know that he is 150 feet away from that spotlight. Using this, we can figure out what the height of the cloud is. For example, we know this, we know the angle, we know h. So this is a perfect cosine situation. The cosine of 68.2 is going to be equal to the height, the opposite. Oh, sorry, I meant to do not cosine, but tangent. Because this would be, I want height, and I know the adjacent. So we want to find the tangent of 68.2, and we're going to divide h by that 150. So this is my opposite over adjacent. TOA, tangent. All right, and solving this then for h means 150 multiplied by the tangent of 68.2. We expect it to be reasonably longer than the 150 feet, just looking at the picture, but you can't always tell by pictures. Sometimes, especially if you're drawing them, we don't really know how high that is because we're not there. But 150 times the tangent of 68.2 gives me 375. Well, if we rounded it to one decimal place, 0.0, because there is a 0 there. And this would be in feet. So we would estimate that the cloud is about 375 feet off the ground. Looking at another example, similar thing, but we're located on a mountain. We know the height of the mountain we're on over here, that it's 8,720 feet above sea level. And then we have another point up here we want to measure, and we want to know what the height difference is, right? So a surveyor wants to measure the height of Mount Kilimanjaro by using the known height of a nearby mountain. The nearby mountain is at an altitude of 8,720 feet. The distance between that location and Mount Kilimanjaro's peak is 4.9941 miles. And the angle of elevation from the lower location is 23.75. Use this information to find the approximate height of Mount Kilimanjaro. So we want to first find h. So we're given over here, we're given this distance, which is the hypotenuse, and we want to find the height, which to this angle that we know is the opposite over hypotenuse. This is a perfect sine situation. The sine of 23.75 is equal to my height divided by 49941. Oh, wait, I did something wrong there. Oh, 4.9941 miles. That would be a lot of miles there. There's a decimal there. So height obviously is going to be equal to 4.9941 miles times the sine of 23.75. We can go ahead and type that into our calculators. Should get a height of about 2 miles. So it's my mountain here, 2 miles above sea level. Well, of course not. It's just, let's see. It's 2 miles higher than the other peak, right? But we also need to figure out how many miles this is, or if we want to put it into feet, we can put it into feet. I'm going to do it both ways so we can see that. What we need to know is what the measurement between feet and miles is. 1 mile, and this may not be something you remember, but it's 5,280 feet, 5,280 feet. And, of course, in the English system, we just have all these very strange measurements that we use that we can't seem to get away from. So if I want to convert this over to feet, I'm going to take my 2 miles and I'm going to multiply it by something that gets rid of my feet. So I'm going to put miles in the denominator since miles is in the numerator here, and then 5,280 feet up here. This tells me that To do it, I need to multiply 5280 by 2, and that'll give me 10,560 feet. That's a comma there. Well, that's not, again, that's just the 2 miles height. We would need to add this to the 8720 feet that the other mountain is, that it's 2 miles above. So that gives me 2, 8, 12, so 19,280 feet would be the height of that mountain. If we want to put that into miles, let's change those feet into miles. I'll take those 19,280 feet, put it over 1, and multiply by the reciprocal unit thing, where we have 1 mile on top, and we have the 5280 feet that we want to get rid of on the bottom. So if I divide, essentially, 19,280 by 5280, I have the miles. This comes out to be 3.652 miles. So there we have it. There's using trigonometry to get other measurements. All right, here's another one with a river. To find the width of a river, a survey sets sites across from the river from a point A on her side to a point B on the opposite side. A very specific point where she's making a 90-degree angle. Then she walks 200 feet upstream to point C, and the angle that she looks at there from that point to B is 58 degrees. I'm going to write that in there. 58 degrees. How wide is the river? So our big thing is to figure out how wide the river is. Notice that she was able to measure how far this is, and was able to measure the angle at which to the bank she would have to look to CB. So this is an adjacent side to that, and W is the opposite side. So the tangent we know we can use of 58 degrees should be equal to my opposite, so W over 200. So here we're using the opposite over adjacent, multiplying both sides by 200. We get W, the width is 200 times tangent of 58 degrees. Which is 320.1. 320.1, and I'm assuming that's in feet. Yes, it is in feet. That would be the width of the river. So here we're given another problem. This is our last one, and it looks like we're after an angle in this one. A security camera is to be installed 40 feet away from the center of a jewelry counter. The counter is 30 feet long. At what angle to the nearest degree should the camera rotate through so that it scans the entire counter? So here's our camera. It's set at the very center of this. We know the cameras, or the width of the counter, is 30 feet, and so half of it, where it's centered, is at 15 feet. And we also know this. So I can assume, since we're just scanning from the middle, that these two angles, right, are going to be the same. And I can figure out what this angle is, and then I believe this is what it's set at, so then it would just need to scan the same amount. If it's looking over here, and how far does it have to rotate to catch all of this? Well, it's going to rotate the same amount if we're set at the center here. So, since I know the opposite and adjacent of theta, That's, again, another tangent thing. And I know that, so tangent of theta is equal to 15 over 40, opposite over adjacent. To find theta, then, we're going to take the anti-tangent, or the tan inverse, of 15 over 40. And that gives me 20.56 degrees. And I got this big old line in the way there, so just ignore that. 20.56 degrees. I'm not crossing that out because it's incorrect. That would be this. And so we can assume that these are going to be the same angles. And that's it for this. Practice using these trigonometric functions in your story problems on the homework tonight.